do electromagnetic induction. Or continue it if you want. So, it was noticed many years ago that there's some sort of relationship between electricity and magnetism. We did go into a little bit of what the nature of that might be, and the fact that moving charge generates an electric field around it, or sorry, a magnetic field around it. So let's just remind ourselves of what that's going to look like. So if we say this is a current carrying piece of wire, okay, a cross section of it or a piece of it, and there's a current flowing through the wire. In this case, we'll say it's here. And remember, in our world of physics, we're going to go with a plus to minus flow of current. Again, we realize that in reality, it's actually electrons flowing. But anyway, this is how we would have a flow of current in this wire. And we learned by placing magnets around this very scenario that the compasses that we put will point essentially like this back around in this manner. Okay, so we end up with this circular magnetic field, and an interesting way to think about that is like a flag in a wind. Okay, so if you imagine the little mini compasses, these little mini magnets sitting on their pivots, if you imagine them to be like a flag, okay, well, the flag would point in such a way that it would react to this quote-unquote magnetic wind, if you want. Okay, so that always helps me to think about what's going on here. All right. Now, this is a little bit cumbersome to draw it like this, so we came up with a method of showing magnetic fields. And when the magnetic field's going away from you, we draw X's. Okay. So we know that these X's mean in this plane, in the plane of the page, in the two dimensions that we have to work with, the field points away here and towards us here. The X's were like the tail feathers of an arrow that we've shot away from us, and the points of the arrow coming towards us look like dots. And we use the right hand rule number 1 to show this, where the thumb of our hand points in the direction of I, and our fingers, oops, it's kind of a funny finger, wraps around to show the magnetic field, okay? So that's B. All right, so that's how we kind of remember this. We imagine taking our right hand and wrapping it around this wire, okay? We also demonstrated today that there's a relationship between a moving magnetic field and electric current generated, okay? So before we get to that, let's talk a little bit about what a solenoid is. And a solenoid is a coil of current carrying wire that basically sets up a magnetic field within itself. What was the symbol that we used for magnetic field again, by the way? That's right, I drew it over here. It's B. Okay, B is the symbol for magnetic field. A little bit later, we'll get into what units B is measured in, but for now, the symbol of it is just going to be B. So a coil of wire that sets up a magnetic field within itself. Okay, so if we run current through a solenoid, and I'll draw one here, so what I'm going to actually do to help us visualize this is I'm going to draw a bar magnet. Okay, now this bar magnet you have to think is imaginary. It's not really there. A solenoid is just a coil of wire with air in the middle of it. Okay, you can have iron core solenoids, but we're just going to talk about an air core solenoid. And we're going to imagine that there's some wire wrapped around it like this. Okay, it's much easier to understand what the coils are doing if we do it this way, I find. Okay, there. Now we'll make this positive and this negative, so we've hooked this up to a battery, and we've got a flow through here. Okay. So our current, in this case, is flowing, if you want, upwards. All right. Now let's think about what would happen if we were to look at the way this current is flowing, and we were going to go back up to what happens in a single wire. Well, our thumb is going to point the direction the current is flowing, and our fingers are going to make the magnetic field that exists around that. So let's take this last piece of coil. Imagine our thumb is pointing up, and then our fingers are curling inside the magnetic field, or sorry, inside the solenoid. Well, what that's going to kind of show you is that the magnetic field is going to be going kind of like this, right? It's going to be heading into the loop, and because these coils are set up next to each other, their magnetic fields interact and build up. Each one adds a bit, adds a bit, adds a bit, adds a bit. And at the end of the day, you're going to have your magnetic field kind of spewing out the other end. All right. Now we know from past practice that a compass will point away from a north and it will point towards a south. Again, that wind concept, right? The wind blows out of the north and into the south. So our solenoid, we can predict what the magnet it's going to create, what the electromagnet it's going to create is like, simply based on the way that we run the current through it. Okay? And remember that our cheater way of figuring out which way is north is just imagine taking your hand and grabbing with your fingers pointing in the direction of the current, and if you use your right hand, your thumb will point to the north. Okay, so if the current is flowing that way, and you just grasp onto the solenoid like you're gripping a baseball bat or something, your thumb will point to the north. Okay, so two ways of doing it. This right hand rule that we all kind of know is one way, or you can use the, if you want, cheater or shortcut rule for a solenoid. Okay, so far so good. That's what a solenoid does. Creates a magnetic field inside of its coils. All right. The more coils you have, or the higher the current is, the stronger the field, or the smaller the cross-sectional area. Okay. There's a lot of physics to do with sorting out what size and strength this magnetic field will be. You don't actually have to learn any of that. So for another time and place, we can learn the math on that part of things. Okay. So we know then that running charged particles around and around and around this coil, and again we imagine they're positive charged particles, creates a magnetic field. So people back in the day, in the days of like Michael Faraday, who did a lot of experimentation with solenoids and electricity, we also learned that if you were to flux or to move a magnet within the solenoid, it will actually set up a current. Okay, so let's quickly talk about that. All right, so if I have a coil, let's just redraw sort of what we had up there. Okay, so here's our imaginary bar magnet. It's not actually there. It's just to help us draw and understand what's going on. And here's our solenoid wire. Okay. Sorry, my bad. I don't want to actually put current in here yet. What I want to do is I want to attach this to basically to an ammeter, but not quite an ammeter, a galvanometer. One of the main differences is that a galvanometer can show potential in either direction, right? So what's going to happen here is right now we have no current flowing, and let's say we take an external magnet, right? Now this is a real magnet, okay? It would help if we were to just kind of erase this out or kind of fade it out so we're kind of a little bit more understanding that there's not actually anything in there. I hope that makes sense to you guys. It's a little bit not that easy to understand, but probably better when it was there. Okay, well, whatever. If this happens to be the north side of the magnet, okay, well, what ends up happening, right, is we've got these field lines here. And if we apply a force and bring this magnet in here, and you have to apply a force, right? You bring this magnet in here. Well, what ends up happening is in that sort of interior imaginary electromagnet, the induced electromagnet sets up in such a way that it will repulse this incoming magnet. So in other words, I have to do work, right? And I have to do work over a distance. I have to apply a force over a distance, which is work, right? If I'm doing work to jam this in here, all right, that is registering as an electric potential down here, right, on the galvanometer. Okay, and it's going to move back and forth. As I insert this in, this sets up such to oppose the flux change, and we'll talk about flux in a minute, but flux is essentially the magnetic field, or the density of the magnetic field. If the density of this magnetic field is changing, okay, what that's doing is it's imposing force on the charges inherent in the wire, and they're going to react to it in such a way that they're going to attempt to move, right? That electric field, or that magnetic field, is going to make them attempt to move, okay? The way they move sets up a converse magnetic field, right, that opposes that motion. So let's think about if we do this. If we jam this field towards, we're going to feel resistance. That must mean that this solenoid is setting up in such a way that a north pole is happening on the right side. So which way do we expect current must be flowing in the wire as we bring this into the field? Which way do you think? We have north on the right side of this particular solenoid. How is that working? I don't quite understand. Like this, you mean? So we must have current flowing this way, right? If we think about our rules that we looked at, okay, if we think about the rules that we looked at earlier, okay, the solenoid, if it has a north pole on the right, the current must be flowing. Think about grabbing it with your hand and having your thumb point to the right. You have to reach behind, and this side to be north must have a current flowing this way. So in other words, this acts as a positive, and this acts as a negative in this scenario. Now, let's think about what happens, and I'll redraw one more, which is a little bit later, when we start to draw our real magnet away now, okay? So now we're changing our flux, but the opposite way, okay? So now what's happening is our flux, oops, why did I make that south? That wasn't very smart. Now what we're saying is we're drawing the flux away here. Let's just finish drawing all this stuff because it just takes a second. And we'll say that the velocity is now this way, okay? And just redraw this correctly if we can. Oops, I accidentally put an extra coil. Please ignore the extra coil. What do you think adding extra coils would do, by the way? What do you think reaction to all of this would happen if I put a bunch of extra coils on but did the same thing with the magnets, moving them back and forth? Yeah, I would increase the potential that I would show on my galvanometer here, okay? So now what I'm doing is, before I was pushing this in, and this was setting up such to resist that change, now I'm pulling it away. It also wants to resist the change in flux. So how does this spin current such that it resists the removal of this magnet? Which side must become south inside our solenoid? Like attracts. So if I'm pulling it away and I have to be doing work when I'm pulling it away, which way becomes south and which way becomes north? Well, to resist pulling away, there must be an attraction here, right? It's got to be attracted, and if I'm working to pull it away, this must set up in the south. So in other words, what that must do is it must change the direction of my current, right? Now my fingers will be pointing up. My thumb would be pointing this way towards the north, okay? Current, I, is now flowing this way around my system. Or potential is attempting to push current that way. I should be careful. You may not actually have a current flowing, right? If you have something like a voltmeter on here, it's just showing potential. Until you actually complete the circuit, you may not actually have any flow, okay? Whatever though, that's sort of irrelevant. If this were completed and we move this back and forth continuously, basically you have like a wave of electrons inside sloshing back and forth. Like if I were to take, say, a bowl of water and tilt it either way. First it rushes one way, then it rushes the other way, okay? Does that make sense? So here really is everything you need to know about generating electricity with bar magnets and coils. Now, is that all you need to know about generating electricity, period? Obviously not. But this is a nice starting point to think about the interaction between these two things and how it is that you can actually generate a potential and where the work is coming from to make that potential happen. Remember, you can't get your money for nothing, right? You can't get energy for nothing. Without doing work, no energy. All right, let's move on from this. It turns out that we're only looking at like sort of half the information at this point, okay? What were to happen if we were to take a magnetic field and we were to take some charge and fire it in or flow it into an existing magnetic field? What do you think would happen in that scenario? Okay, I don't know who's ever seen a picture like this before. Maybe none of you. One place that you may have seen it in pop culture, although I'm probably dating myself a little bit, there's a famous album cover that has this picture on, and it's by The Strokes, and I'm just going to take a second and find that. So just for interest's sake, I grabbed that album cover. I don't know who listens to The Strokes these days, but anyway, there's their album cover. So what this is representing actually is the output of something like a collider, so like a nuclear accelerator. So essentially what would be going on here is you might take some sort of heavier particle, maybe a proton, maybe even an atom, accelerate it to super high velocities and have it smash into some sort of other matter, with the hope that it would basically burst and fire out charged particles. Now this collision and explosion of charged particles would happen in a chamber that that has a large magnetic field in it. And using techniques I don't understand, what scientists are able to do is they're able to visualize the arcs and paths of electrically charged particles shooting out from that explosion, okay, in something called like a bubble chamber. All right, I don't know, there might be more obviously sophisticated techniques nowadays, like in the LHC. I believe this happens in something called the Atlas detector. Again, I could be wrong, but I think that is. And anyway, they visualize the tracks of these charged particles, measure them, look at which way they're arcing and spinning, and you're able to tell all kinds of information based on how tight these coils are. I mean, that might tell you stuff like mass and velocity and so on. The charge on the particle would be dictated by which way it curls. So the question is, right, how is this working? All right, and it turns out that there are essentially three vectors going on when you're talking about electromagnetism, okay? There's the direction, the vector direction of the magnetic field. There is the vector direction of the velocity of a charged particle, and then there's also a force exerted on that particle, okay? We already understand, and it's no surprise, that magnets can exert a force on other magnets, right? And moving charged particles, we already learned, exert a magnetic field themselves just by virtue of moving through space. So it should make sense that if a charged particle is moving, it's got a magnetic field around it, and if there's an external magnetic field, those two things will interact and create force, magnetic force, on the particle, right? So now all we have to do is just deduce how that's going to work. So what we'll do is we'll draw, that's the background. What we'll do is we'll draw a chamber that's meant to represent a magnetic field. So what we'll do to help our brains wrap around this, because it's a little bit maybe possibly tough to understand, is we'll use a horseshoe magnet first, okay? So let's imagine we have a horseshoe magnet. What would the field inside a horseshoe magnet look like, the magnetic field? Inside it, in this area, what would it look like? Put a compass in there, use your brain and just use your imagination to put a compass in there. What's it going to do? Perfect. That's what a compass is going to do. That's what the field will do. Don't worry about outside here. I don't care about that. Now imagine, okay, that this like extends back into space, okay? So it goes back and it's like a big, long horseshoe. Like something that we probably wouldn't really often interact with. I don't even know if something like this actually really exists. Maybe you got a whole bunch lined up, I'm not sure. So anyway, we've got this long area inside here with this consistent magnetic field. And now imagine that we're able to actually get inside here ourselves. So we're sticking our head in here and we're lining ourselves up with the magnetic field to see what it looks like. Okay? So here's kind of like the outside view. Now what I want to do is I want to imagine, okay, I'm inside and I'm looking from north to south. So north is behind my head, south is in front of me. I would see a magnetic field that's like this, right? Pointing away from me. North's behind my head, south's ahead of me. It's like arrows shooting away from me through my head. Are you with me? Now let's imagine that we fire into this field some charged particles, okay? And let's imagine that they're positive. So somehow we're injecting some positive particles, free positive particles, let's say protons, or alpha particles or something like that. We're firing them in there with some velocity, okay? So what ends up happening, here they come entering from the right. Well, these positive particles around them, okay, they're setting up their own magnetic field, right? So in they come. Now what we're going to do is we're going to use our right-hand rule to explain what type of curl or curve is going to happen. So here's how we do it. Take your pointer fingers. Do this right now. Point your fingers in the direction of the magnetic field. Okay? So in this case, that's into the page. So you're going to point your fingers towards the page, towards your screen. Your thumb, that's going to point in the direction of current, like it did before, or the direction of positive charge flow. Now look at your palm. Your palm points the direction of force. So in this case, force will be where? Up. Perfect. A positive charge injected into a magnetic field in this way experiences a force in this direction, and it will tend to curl in that direction. If we can visualize it, we might get something like this appearing. Do I see one curling up? Yeah, like this one here maybe. Or these ones here, right? Up they go. So if this were in a bubble chamber set up the way we've drawn it, we can know these would be positive charges. If they're entering from the left and they're curling this way, whatever this is positively charged. Are you with me? If it has a really tight coil, what can we say about its mass? Smaller or larger than, say, one with a big curve? The smaller one, right, is probably lighter if they have the same momentum at the beginning, okay? But we're not sure about that. So, I mean, I'm not sure. You might be right. Maybe it's larger, but it's moving more slowly or something. So then it would have a tighter coil, right? But it in general, if they came in at the same speed, the lighter one would have a tighter coil. But do we know that? I don't know. Okay. So what do you think happens if we were to inject it this way? How do we do that? Well, fingertips point magnetic field. Thumb points direction of velocity of charged particles. Palm points direction of force, and we would end up with that, right? So we end up with a force down like that. So you can imagine this. Now, what do you think happens if we put a negative charge in? Well, I'll tell you what. You do the exact same thing. However, you just switch the direction of force. That's all. Okay? Positive force points up. Well, negative, just the opposite is going to happen. So if it were positive, it would curl to the left, but it's negative, so it's going to curl off to the right. So force goes that way. And that's it. That's all there is to how charged particles behave in magnetic fields. If you were to switch the direction of the field, like say we were to like look at it from this side, obviously now your fingertips are just going to point out, your thumb's still going to do what it does, and your palm's still going to do what it does. Okay? So everything will just work itself out. If you use your left hand, you're in big trouble. If I were to walk by and peek in the window while you were writing a test, and I see anybody's left hand up in the air, I know I've failed. Right hand rules always. Okay? So last thing, how can we generate a useful force with this understanding? Well, one thing we can do is instead of injecting, say, a vacuum, free charged particles, why don't we just flow charged particles through here, a wire? What would happen then? So let's imagine here that we have this scenario. Let's say we have 2 copper pipes. Why? Because we can get copper pipes if they ever actually wanted to build something like this. So we have 2 copper pipes. It's going to be 3 copper pipes in a minute, but so here's a couple copper pipes. Okay. Now let's say we took another copper pipe. This doesn't need to be a copper pipe, but I find it easy to imagine if it is a copper pipe. Okay. Maybe it's just copper wires. Who knows? I like saying copper pipe. And then on top of this, these 2 copper pipe rails, I have another piece of copper pipe. Okay. So this is now free to roll. We're looking down on this from above. Are you with me? Let's say now we put a magnetic field on this whole scenario. Okay, we put this all into our big magnet. Okay, so this magnetic field now we're imagining is pointing out of the page towards us, right? If it's pointing towards us, that means north is back here and south is behind our head, right? And let's say we hook this up to a battery. Here's our battery. And here's positive and here's negative. And we attach this or clip it onto this rail. And we clip it onto this rail. Okay? Now, if we look, current passes from positive in and out through negative. So in other words, inside this wire right now, we're going to have current pointing that way. Now, my question to you, while this current is flowing with the influence of the magnetic field, there will be a force exerted on this free-to-move copper pipe, right? See, these are 2 rails. We'll imagine they're fixed, and this copper pipe is free to move. We're looking down from above on this, okay? Perfectly level. Which way do you expect the copper pipe to move? Which way will it move? Current's flowing to the right. Current represents positive charge flowing along this way. Which way is force going to be exerted? Get your right hand out. Point your fingers in direction of B, the magnetic field. Well, that's out of the page towards your face. Point your thumb in the direction of the current flow. So what you should be doing right now is this, right? Your hand should match my hand. Okay? Which way will this copper pipe feel a force on? Up or down? Down. Excellent. My hand is not upside down. Because my fingers, these things, my phalanges, point in the direction of the magnetic field. That's towards me. Out of the page towards me. That's what the dots represent, like someone shot an arrow towards me. My thumb points the direction that positive charge is flowing. And my palm points the force. This will tend to roll, and will physically roll down these rails towards me. If I flip the switch, or I flip the battery, and I flow current the opposite way, it will roll up. If I flip the field, it will roll in the opposite direction. You can make yourself basically a very simple method of moving objects with a few horseshoe magnets and a couple of pieces of copper, and this will work, and anyone can do this at home if they really wanted to, okay? This is not a practical motor at all, okay? However, imagine now that instead of just having one conductor, we have a coil of conductors, right? And we're able to flip-flop the direction that we move charge in this flip-flop, in this now solenoid, and we're able to suspend that inside a magnetic field. Well, what you would do is you would end up causing it to spin. Rather than to roll back and forth, you can cause it to spin, right? And that basically is now a practical electric motor. It runs on the same principle. You just have to engineer a way to have this happen inside a magnetic field in a practical way. But at its simplest, if I want to move a piece of coil, this is a way to do it, okay? And there is math with this now, okay? We can actually detect the force, and here's the formula that helps you do this. The force, the magnetic force, is equal to B-I-L sine theta, okay? So what do these things represent? B, that's the force in newtons. Okay, B, that's the magnetic field strength. We'll talk about what that is in a minute. And that is measured in Tesla. Okay, we'll talk about what a Tesla is in a minute. And L, that's the length of the current conducting piece of wire, or in this case, copper tubing. L, length of tube in, meters. Length of tube in meters. Okay, and then sine theta. Why is there a sine theta, do you think, on this? It's not so much about work. It's about the interaction between the magnetism that this current is setting up and the magnetism of the permanent magnet. Look at your hand right now. What does that actually represent? It represents that the magnetic field and the velocity, or the direction of current, are at right angles to each other, and that the magnetic force is at a right angle to both of those. So in three-dimensional space, all of these vectors basically act at right angles to each other. If you were to inject a charged particle in such a way that it were moving in line with the magnetic field, then the two magnetic fields would not interact in such a way to produce a force, right? If I were to take this magnetic field and put it in line with the current, well, then this flowing charges magnetic field and the magnetic field would not interact to repel one another, okay? So what the sine theta here is it's saying that this works fully at 90 degrees, right? Because sine 90 is 1, right? So when my current and my magnetic field are at 90 degrees to one another, I get full force. If they're at some other angle, it's only the component that's perpendicular to the field that's producing any force, right? So if instead of having this at 90, I were to take it and rotate it, in, say, this plane, okay, such now that current was, say, only 45 degrees, well, I'm going to get a halving of the amount of force. If I turn it 90 degrees such that the current and the field are in the same plane, I get 0 magnetic force. That's what the sine covers. Does that make sense? That's a reaction of our universe. So let's just quickly do a super quick problem. Okay, find the force on a 1 amp wire, 1 meter long, in a 1 Tesla magnetic field, where current is 90 degrees field. Well, what's the answer? It's going to be 1. 1 times 1 times 1. So it's 1 Newton. Now, why do you think I gave you this? Well, I gave you this because this is going to help us understand what a Tesla is to begin with, okay? Or the definition of a Tesla, okay? And what its units are at the end of the day, okay? So if we look at this, FB equals BIL sine theta. Well, sine theta has no units, right? It's just sine theta. What we want to know is we want to figure out, how do we define magnetic field strength? And it's actually defined based on the interaction between current carrying wire and the current going through it, right? So B then, if we look here, could be defined as force over I times L. So if we want to find out what units this actually is, if we want to break it down to its base units, well, we've got newtons on top, and we've got current in amps and meters. So there's one way to define it. Newtons over amp meters. And the way we would properly write that, of course, is this. There's one definition, but that's not broken down to full SI yet, right? Because we've got to break newtons down too, don't we? This is an SI unit. This is an SI unit. This is a combined unit. So how do we do newtons again? That's right, kilogram meters per second squared over amps over meters. So if we look, cross that off, and there should be your SI units for this. Kilograms per second squared over amps, or kilograms per amps per second squared. Okay, well, it's kind of like a goofy unit, really, at the end of the day. What's it saying? I think the best way to think about it is it's just saying a magnetic field of 1 Tesla creates a force of 1 Newton if a 1 amp charge flows through a 1 meter wire. Okay? If it forms a 2 Newton force, then it must be a 2 Tesla magnetic field, and so on. Okay? So this is the definition of the Tesla. It's basically defined on how much force occurs based on the magnet and the current flowing through it. Okay? Are you good with that? Now, it's unfortunate we don't have enough time to go into like fluxing and generating electricity and so on. But this is kind of like the bare bones introduction to it, and this is all you really need at this point in your career. So, thanks.